Hey, good afternoon, everyone. My name is Jeff Schrader. I'm your session chair, and my co-chair is Jim Sims, back in the corner over here. I'm an IPP developer and due diligence consultant based in the Dallas area. My company is Genova Power, and Jim is the VP of Business Development for Vote, and so we've been successfully chairing this session now for about more than a decade, and we're always pleased to have the OEMs talk about a topic of interest in natural gas-fired combined cycles. And today we're also joined by a user owner, and we're excited about that. As we develop the session, we try to come up with an idea or theme over the years that we've looked at that are current topics, such as a few years ago we were really getting into rapid starts and lower starting emissions. And the theme this year is to head more towards single shaft combined cycles. What's happened as we've gone to the advanced technology turbines, they've gotten so large that it's very difficult for users to actually have a need for greater than 1,000 megawatts of combined cycle in one episode, and also the capital required approaches $1 billion when you start to do that. So we're going to take the panelists in order today. We're going to have time at the end for roundtable discussion, and it's always exciting to do that because we could ask everyone. I'll also mention that it's if you have a really pressing question during the middle of one of the panelist sessions, it's okay to raise your hand and ask while if it's something you think that would be interest to the whole group to clarify. Otherwise, I'd ask you if it's a more general question to save it until the end. We're going to take, like I said, everyone in order, and the reason we do that is some of you guys may want to pop in and out and go to, we hope you don't leave, but some of you may see something on the program that attracts your interest at 2:15 or I'm sorry, at 2:45 this afternoon or something and make you leave on us. Let me start off with our first panelist, David McDeed. David's Senior Project Manager at Mitsubishi Hitachi Power Systems, and for large gas turbine combined cycle equipment. And he's functioned in that role since the middle of 2016. He focuses on supporting project development to meet the market needs, supporting the sales group on information requests, and the technical group on economic product improvements. Prior to that role, David was the manager of applications engineering, where he and his team are responsible for engineering and technical evaluations to support new equipment bids, and responsible for site tuning and performance equipment since 2001. Prior experiences to that is it started in 1993 with positions at Westinghouse, where he focused on auxiliary design, tech publications, and then Siemens on applications engineering. Lastly, he did a stint at Enron, where he spent 3 years in project development in the U.S., Europe, and South America. David brings 30 years of experience in the power industry, both as an OEM and as an IPP. He has a Bachelor of Mechanical Engineering from UCF, and he's been active in ASME. David.
Thank you, Jeff. Thank you, Jeff, and welcome everybody to the session here. Let me get the piece parts here. Hey, Jim, do you have a clicker for this thing? I think I'll probably just use the mouse or use the button here. Okay, good afternoon, and I hope everybody enjoyed the keynote session this morning as far as the discussions there. And can you all hear me well enough in the back? I'm not quite hearing myself that well.
Closer if you can.
I guess I'll just squat down. Get shorter. Okay, hopefully this here is, yeah, I can hear myself coming back a little better to me. Yeah, I guess I've done this for a couple of years, and I guess with Jeff, it's nice that he rotates the order, because one year you go third and you have the 3 OEMs up here. It does get kind of as far as saying, yeah, we too kind of a thing. So try to break it up this year and do a little bit different with my presentation, but still have the same theme, the proper themes coming into it a little bit here. You might notice this this wild racing shirt I've got on. We are selling them, you know, at the booth to help subsidize for the way the gas turbine market is these days. But no, as far as this is the revolution, it's an introduction to our marketing strategy we've had started last year, and we're continuing on. Right now, it's not just the, well, I don't want to tell my slide earlier, but we're continuing on in the revolution. I'll be explaining it here. One piece of that is that you can get up to over 64% efficiency now in combined cycles as far as the power equipment goes. And just talking here recently with some friends of mine, 10 years ago, these numbers seemed like astronomical, but now they are within reach and coming up in the very near future. We have over 468,000 actual operating hours on our J fleet at this time. Okay, it first came out as a steam cooled. This is a process we've gone through, and I'll go through a bit more later, of introducing high temperature, high technology equipment coming out. First is steam cooled, because it's easier to use steam at first until air cooled technology gets to the level to where you can get that same temperature, so you can get the better efficiency even with air cooling. And over 99% reliability. Our J fleet, as like our G fleet, has over 99% reliability in operation to date with the equipment. We can ramp at roughly 50 megawatts an hour, megawatts a minute. Significant difference there, to keep up with the larger dispatch, the way the grid is moving these days for quicker response. And also we can get down to 20% load with our gas turbines now, which help out significantly as far as the renewable backing and the way that, you know, renewables coming up very quick and balancing out grids. But what started this revolution? When we go back and take a look at the way gas turbines have been developing for the past couple decades, of having the experience I've had in the industry, I've kind of watched them. Luckily, I got in gas turbines early on in my career and have seen them grow from the D class. I first started getting involved with the beginnings of the F class. And when the F class was introduced, it replaced the D and E class, similar to that chart Browning showed this morning. I'll be showing one here too, and how the transition has always been driven by efficiency with gas turbines. With the problems that we had with the F class rolling out, which we as an industry had as far as the technology, Mitsubishi learned that we need to demonstrate that technology within our bailiwick first on a long-term basis in order to improve the reliability and operability of the machines going forward. Okay? This is that chart I was talking about. Paul's was squished from the top, mine's squished from the side, so you can get a different perspective of it here. But as far as the gold line there shows the D and E class as far as percentage of market space. And as you can see, it started back in the 80s. The F class was introduced in the late 80s and started taking over the market, and pretty much around 93 or so it took over the market. Then the advanced class machines were introduced. They're in the middle 90s. They were introduced and started taking some market share. And then here recently, just a few years ago, we introduced the latest versions of those as far as the latest advanced class technology engines. And with that, the precipitous demise of the F-class machines as it goes forward. Right now, you can currently get these types of machines, and this is what we're calling the advanced class gas turbines, ACGTs. The latest version and our G version from the previous machines coming out in the 90s is still available for purchase today from all the OEMs. Okay. Field validation legacy. As I mentioned, when the F-class was rolled out, there were some significant problems in that learning curve of the 80s and 90s of those machines. Some reports that chronicled that. ASME reports were put together. One's listed there. You can go take a look at it. They were saying that the availability of the fleet was roughly 7% worse. If you look at the dates, that's about 10 years after the machine was introduced. The data coming off, as far as RAM goes, tracked by Strategic Power Systems, I think it was at this time, third-party independent validating of technology, show that availability of F-class machines was significantly worse than D-class. For a slightly different time period, Turbo Machinery International put out an article saying it was 4% worse. So some consistency there. And then in 2007 timeframe, an ASME paper came out that was quite exhaustive as far as the study goes, and taking a look at it over the years, determined that in 98, availability dropped down to 76% on the F-class machines in comparison to over 90% on the D and E class machines. That's roughly 10, 15 years after that technology was introduced, proving out that at that time all the OEMs were scrambling, basically, to get problems fixed that were significant design flaws in the equipment. They were renting space on one of the Antonovs in order to fly rotors around the world to fix fundamental design issues on the rotors. Okay? So new technology always has rollout issues. There's always going to be problems with it, and we learned that from that time frame, that we need to be doing a more robust study or validation of the technology. There's some other reports listed there that talk about this very same issue. So it's a pretty well documented issue overall in industry. Also, the International Association of Engineering Insurers did a study in 2009 timeframe where they looked back over the same data. They came up with different categories or failure modes. Here they're showing 11 of the design type. They have also another batch that talks about operation, another batch that talks about service, and so on. But if you look down this list of these items, you'll see here, I put on the right side there where it's validation. Only one of them is caught with short-term validation for a couple hundred hours at a site, a test bed. The rest of them will only materialize or metastasize after thousands of hours of operation. I underlined the one there talking about rotor issues, because I'll come back to that issue here in the near future specifically, but again, you only see that in long-term validation. Mitsubishi's, this portion of this chart is correct even back to the F class, but we've modified it since then due to the F class. But up in the top left corner up there, you can see how we do the validation, whatever computer simulations we can do, and then we take it and do test bench type validation to prove that the laws of physics and reality are matching what we're saying in the theoretical, as mentioned earlier this morning too. We then roll over and design that technology into the machines, balance it out and then manufacture the components. We would then do some form of short-term testing of that equipment and technology to verify that it runs, work out any issues, and promote it and produce it from there. But what we started doing now is rolling over and doing some long-term validation at T-point also, driving the machine for thousands of hours before we sell or before we deliver the first machine to a customer. That's serial number 2 and on. What that allows us basically is to do any kind of design improvements that we see where we can get some easy improvements and or fix any problems that we see if we have spalations. And the nicest thing about this is that this is all on one facility. So the T-point facility in the top left corner of that map is not far from the R&D center, which is not far from manufacturing or engineering, okay, and design. So all the groups can talk to each other and coordinate and find out if this is a manufacturing issue, is it a design issue, and so on, and get the cause of the problem and ultimately be able to resolve the problem much quicker. We're not having a schedule with a customer to take a plant down, to take it apart, to pull a piece, to fly that piece back to our facility, then start testing it. Everything is at one shop, so it's very quick. It's a 5-minute bicycle ride across that facility, okay? So that incorporates a very quick response to fixing any concerns or issues that we have with that first serial number 1. And that is the final step in the validation before the technology goes commercial, okay, to other customers. Another piece about RAM. Here's a simple ISO of our machine and with the inlet filter house on it. On these latest machines, higher efficiency power plants mean that you have to have a higher turbine inlet temperature. Fundamental laws of thermodynamics. With the way machines are now with the large frames and the high exhaust temperatures, that means you have to have a higher turbine inlet pressure to match in order to keep the temperature down for material issues on the HRSG. That higher pressure ratio means you have a higher higher compressor discharge temperature also. So that higher compressor discharge temperature will then have effect on the cooling characteristics of the gas turbine inside the hot gas path parts. If we take option A and do not do any cooling of that compressor discharge air, we have hotter air going to the components. Therefore, the temperature of those components is higher, okay? That means that we need to start considering more exotic materials for the gas turbine components, be they ring, discs, seals, blades, and vanes that are operating at higher temperatures in order to be able to operate long terms. And it does have some additional failure modes with those types of materials we've seen. Or we do option B. We use coolers. We cool the compressor discharge air down to a more reasonable temperature, use it for cooling. We use less cooling air so we can get more efficiency that way. But also the metal temperatures are down the same D and E class machine components that we've used and have lots of experience with that are a bit more robust overall in operation and longer lasting. So there are less failure modes, there's a few less failure modes with the older technology, lower temperature materials. Okay. Combined Cycle Journal, just online, put together this article here. Gas turbine checking turbine wheels for cracks during hot gas paths or major inspections. This highlights the point that I just made earlier about the materials. Okay. If you look down this article, which the web link is there at the bottom, in this article, some of the salient points to take out here basically is with some of the F-class machines, again, that everybody, all the OEMs produced, have some requirements that you thoroughly clean and check the discs every so often to make sure they're not cracking. That one failure mode I mentioned earlier from the insurers that talked about disc liberations. This is where it comes from. Okay, and even in 2017, 3 more units were found with significant cracks developing on the rotor discs due to the characteristics of the Inconel and the way they more easily initiate cracking and propagation of cracking. If you look down here, as far as on this graphic here shows, the first line, black line, is the original design back from '95. The first red one there talks about a fix that came up in 2002, and then 2005 they came in with that purplish line there that finally fixed this problem in this groove that was having significant crack issues. Again, this fix came out 10 years after the machine had started going operational. 14 years roughly, the final fix comes out, and then you start rolling it into the machines. You're talking 2 decades of operation with this potential flaw when you start using these higher and more exotic materials if things aren't done very well overall. So it is just a case of being careful. Also here talking on this graphic showing some more from the same article. Rotor discs are made of high nickel alloys, which are sensitive to high temperatures, surface imperfections. Crack initiation and propagation is a definite issue with them. So again, Mitsubishi's equipment all has coolers for cooling and cooling air in order to keep the temperatures down, so we don't need to use these materials that have this additional failure mode. If we take a look at global experience of our gas turbines, our G-class machine, there are 102 of those machines currently contracted, either on operation. There's like 80, some of them roughly in operation at this time. For the 60 hertz, there's 91 total. 50 hertz is 11. On the J-class machine, we have 45 that have been contracted thus far. 48 contracted thus far, and broken down as shown there too. Again, there's about 23 or 25 of those running now to accommodate over 600,000 actual operating hours. Okay, quite a few of those are in the U.S. And taking a look at as far as the operational, contracted, and technically selected, if we take a look at the globe, you'll see here as far as the ones in Canada, North America, Mexico, Japan, Taiwan, and South Korea, for a total of 26 machines that we have technically selected, 23 machines that are under construction at this time, and 25 machines that are currently in operation globally. Okay, those are all the J-class technologies. Now, stepping over a little bit and comparing single shaft to multi-shaft, okay?
On the J-class, can you give an estimated combined cycle heat rate and maybe what the difference is, maybe fundamental difference between the H and the J? If it's inappropriate, it's okay.
I can talk some of that stuff, but it might get a bit, let's save that one for the end.
All right.
Or after the session even too, as far as it goes. I've got no problem saying it publicly, but that could get quite involved, and I'd rather make sure everybody has time to give their presentations. If you could jump that down. Yep. Quick little comparison here, a summary of it basically, since time is limited here with this presentation. Comparison, multi-shaft versus single shaft. As you can see, in the center is a multi-shaft. To the right is a single shaft. Some base assumptions there as far as both of these, let's pretend, have axial exhausts. If we take a look at performance, typically overall on a performance basis, compared to a multi-shaft, the single shaft has about a 0.1% better performance. That is mainly driven by the generator. As you can see, one big generator will be more efficient than 2 smaller generators. If we take a look as far as operational characteristics, startups with the clutched system as this single shaft has, there really is no difference on a startup for time or requirements for starting. Simple cycle operation is capable with bypass stack on a single shaft. And operational flexibility or complexity, it's kind of arguable both ways, but single shafts have the advantage of only having one grid synchronized to the one generator synchronized to the grid. A lot less auxiliary equipment since a lot of systems are combined. So it does make things a little bit simpler overall. And finally, as far as the main equipment, cost-wise, for the main equipment, you've got one less generator, one less isophase bus, one less step-up transformer, so there's some savings on the main OEM or the main equipment. And if you look at the buildings overall in the BOP, there are some cost savings also. Smaller building footprint, smaller building volume, all saves money as some of the big ones. And then finally there, as far as layout goes, again, smaller buildings, there's about 30% savings in building area and building volume between the two. So if you have to have a building, it's cheaper to do it with a single shaft configuration. And as Jeff mentioned earlier, with the single shafts, with the one-on-one configurations getting up to 500 plus megawatts now, which, while it's big for a traditional gas turbine, it's not big for power plants overall. Rankine cycles are running at 1,000 megawatts a pop at times. It is a lot of power on one shaft, but still it's not huge, like it's 2 gigawatts or something along those lines. And taking a look at our experience as far as with single shafts. The US, we've got, North America, we have 1, Europe there's 14, Middle East is 4, Asia has 33, and in Japan we have 53 single shafts running. Those are all forms of gas turbines, some of the older D and E class machines, F class machines, G class machines, and J class machines. Actually, the first 6 J class, serial numbers 2 through 7, were in single shafts for a specific customer, or Kansai Electric in Japan. Very good relationship there with that long-term customer who sees how we do things and, follows that methodology very well. So we have a lot of experience with single shaft is the point there, and are willing to be selling and promoting it here in the US. Now, stepping over real quick to Timoni, it's the customer portal that we use. We have 24 hours, 7-day-a-week access for any operator to call our operations center. As Paul mentioned, this is a multi-tiered. This is the bottom tier that we've been developing for the past 20 plus years or so. The original facility was in Takasago. We then opened up a facility here 15 plus years ago in Orlando. And we've just opened up one here recently in Korea, since we have several machines in Korea now that are operating. This is where we keep our intellectual prowess on operating the gas turbines and combined cycles for customers. Their guardian angel over their shoulder watching them operate and alerting them to any issues that we see potentially coming up that could creep with them. And then we're rolling this over into getting some software solutions. Again, that first layer there is the ORMC, or the service center, or the remote monitoring centers. Plant-based solutions we're developing with the Timoni system to help run the plant at that level much better. Connective services to help digitalize and improve operations and maintenance. Cognitive agent, which is being developed now to help go over top of those layers, to help optimize the plant operation and balance it out with other plants in your grid, and ultimately getting to a more autonomous type of a power plant that can take care of running better, much like your car. You plug stuff in, or it'll even tell you where the problems are with the machine as it's running. I guess with that, any short questions, or we'll delay that one on the J till a little later?
I'll let you go.
Okay. Thank you.
Thanks, David. There you go. Is this your water? Okay. Great. Let me get set up for the next one here, guys. There we go. Okay. Great. So our second speaker today, Chris, and I'm going to say Mikowski.
You're going to say it just right.
All right. Chris is the product line manager for Siemens. He has 13 years of experience at Siemens, with the majority of his career focused on plant optimization. Prior to joining Siemens, Chris was with Stellar Energy as Director of Business Development, ECI sponsor for Kiewit's Engineering's Oil, Gas, and Chemical Group, and product line manager at Kiewit. And prior to that, he was mechanical project engineer at GE. Chris spent 9 years in the U.S. Navy, starting as a nuclear electrician on submarines and culminating as a Tomahawk Strike officer on a guided missile cruiser. Chris has a BS in engineering from the U.S. Naval Academy. Chris.
Okay, thanks everyone. I'm going to take a step back for a minute, and I know a lot of questions may be on specific component performance, and I'm happy to talk about that too, and I'm sure we will in detail towards the end. But I'm going to take a step back and talk more about a power plant rather than specifically a gas turbine or a steam turbine or whatever it is. I looked at this as betting on combined cycles. So how do we make combined cycle plants more successful this day and age, right? This energy market is challenging. So the two things that I focused on that I'm going to talk through, number one is reducing cost. Obviously that's, why just make it cheaper, right? That's always the answer. But number two is increasing value. So how do we get more out of a combined cycle plant? Whether it's installed and we're asking it to do things that it wasn't necessarily designed for, or how do we design it to do more things, to tap into more markets? That's what I'm going to focus on. So, apologize for our Siemens font isn't on this computer, so it makes it a little bit hard to read. But I'm heavy into animations, so other than this slide, you're going to see a lot of stuff moving around, which it'll be easier to focus on the trends. But these are the points that I'm going to talk through. So optimize modular solutions for maximum value. So at Siemens and throughout the energy industry, modularization is a big buzzword right now, and rightfully so. How do we modularize this stuff, make it repeatable, reduce cost, shift cost from the field where things are risky, there's schedule risk, there's safety risk. How do we do more work in a controlled shop? I'm going to talk about that very briefly. Then flex plants, which respond to changing markets. Like I said, the energy market right now, you guys know this, it's all over the place, right? It's a challenge to be able to make money out there. And the days are gone where, we got an RFP and that said, hey, I need a combined cycle plant. I'm going to start it once a week and I'm going to run it at base load and then I'm going to shut it down once a week. You guys can bid on that? Those days are gone. Or it's, hey, I need a simple cycle peakerage. I just need maximum simple cycle efficiency. I'm going to start it twice a day and for 3 months out of the year. And that's it. I mean, now our discussions with customers are, we'll sit down and say, well, what's the focus? Do we want to maximize baseload efficiency or ramp rate or fast start? And the answer is always yes. Yeah, we want to do all of that. Why not? So I'm going to talk about some of the different features that we have that can do that. And then lastly is innovations that matter. So I'm going to talk briefly about some of the innovations that we go through at Siemens. Now it makes sense if you just look at it from a common sense standpoint. We're not going to spend money on things that don't matter, right? Obviously, that's a no-brainer. But some of the things I'm going to talk about may be a little bit eye-opening for things that we don't think matter, that we think that the market is telling us don't matter, which I'm going to talk about too. Ultimately, the goal is we're leading innovations for future-proof generation. Nobody wants to buy a power plant and have it be obsolete by the time it's already, you go to COD and all of a sudden you're at the bottom now of your, depending on how you do it, you're at the top of your resource stack and you don't get dispatched and your pro forma gets all turned upside down because a newer technology came out while you were building your plant or the market shifted. Obviously, we want to avoid that. So, a scope of supply, the intent is not to read this, but at Siemens, we have different layers of scope of supply you guys are probably familiar with. We can supply just a component, right? A catalog item. We'll take 2 8000Hs or a 9000 HL. We can do that. But then we can step up to scope of supply to be able to include these things. The first one is a package where we can include some auxiliaries. Then we go to a power island where we're talking gas turbine, steam turbine, HRSG, in some cases an ACC. And then normally we jump all the way to the far right in turnkey because in some limited aspects, we will provide turnkey solutions, full turnkey plant solutions. So we've come up with a new concept now to bridge the gap between a power island and a turnkey plant, and that's something that we call Power Core. And what that is basically a modularized power plant. From all of the auxiliaries, everything's modularized, skid-based, so you build it like Lego blocks. Even the pipe rack is fully modularized. We've done this on a couple projects so far, both inside and outside the U.S. And again, like I said in the beginning, the focus is to shift time and cost away from the field where there's a lot of variables. Is it going to rain for the next 3 months? Or, is it going to be too cold? Is it going to be snowing and we can't do this type of work? We shift that focus away and put more of it into the shop. Also, what we're seeing, especially in the U.S., is there's a shortage of skilled labor, skilled advanced welders are on short supply. So more of those welds that we can shift to a shop or a controlled environment on a controlled schedule makes the construction of the power plant go a lot easier. Another one, obviously, is single shaft designs, and I know that we're going to talk about this a lot more as we get through our presentations here, but the concept behind the single shafts, outside of the U.S., these things are incredibly popular. Inside the U.S., they're incredibly not popular. But we're starting to see the trend change. For one-on-ones and a simple cycle, David went through a lot of the pros for it. It's cheaper. It's much smaller footprint, which we're starting to see as a big driver for these is footprint. You know, everybody wants to start talking now about power density. How much power can I get for the least amount of land area that I have to consume? So now we start talking about single shaft and the benefits that it can give you here. The smaller footprint, the simplified maintenance, simplified systems, only one grid connection because there's only one generator. So there's a lot of pros to it, and there's a lot of advances that are being done in this with all of the advanced class gas turbines. Now, this is where I'm going to talk a little bit about where we're spending innovation dollars, which may be eye-opening. This is a chart. On the x-axis is percent load, and on the y-axis is percent efficiency of a combined cycle plant. This is not specific to any turbine. This is a very generic chart that I almost drew by hand. But it's essentially saying as you increase load, you increase efficiency. That's the beauty of combined cycle plants. This is the traditional area of focus, all the way up there at the top right. What's your 100% base load efficiency? That's the first question we get typically asked. And that's in every single RFP. I want you to identify your baseload efficiency. That's what we performance test at, and that's what we pay. Well, we don't, but that's what some people pay LDs for when they don't meet. So when you talk about this now for a short time, maybe 18 months or so, Siemens had the world record holder for the most efficient combined cycle power plant in the world. It was over 61% efficient. So the beauty of that plant, all of the time and the engineering that went into the plant to say, here's the most efficient power plant in the world, Guinness Book of World Records. As soon as we left, you know what they did with that plant? You know what the capacity factor plant of that was last year? 26%. 26%. The most, at a time, the most efficient combined cycle plants in the world is running at a 26% capacity factor. The reason for that? The market's changed. They are no longer a baseload resource. They're no longer requiring for baseload generation. So in their respect, it's a little bit of a waste to put that much emphasis, that much focus on something that ultimately they're not able to capture the benefit of. So what we're seeing now is we're starting to see a shift in the focus. Baseload efficiency will never go away. That's always going to be important. However, we're starting to see that some of the focus, some of the attention needs to be devoted to a little bit left in the scale, because this is where we're starting to see substantial portion of operating time for combined cycle plants. And this is where it sort of breaks off from the usual or from the typical. Plants are now operating at 80% load. They want to maintain that ramp up or ramp down capability or chase wind or whatever the reason is, they want to operate there. So that's where we're starting to shift some focus. In addition to that, we're looking now at the lower end, a lot harder than we were before. How do we drive down that minimum load? How do we give you more turn down so that you can park these combined cycle plants lower at night or during the day or off peak times, whatever it is? And obviously increase start time. We want to spend as little time as possible in that high emission start zone, so we focus a lot of energy there. But the point of this is it always used to be, what's your baseload efficiency? What's your maximum? Who's going to be the first to 65% efficiency? Now, I'll tell you, and don't tell anyone that I said this, especially at our booth, but I think when somebody gets to 65% efficiency, it's going to be a thumbs up. That's fantastic. Now, what is your efficiency at 85% load? And that's going to be more important to people because it's going to be, that's great. I don't need all this power right now. I need the flexibility to be able to ramp from 20% load to 80% load. How efficient and how fast can you bang between 20% and 80%? That's going to be what's important to me, and I think that that's where the industry is going to go. So baseload efficiency is going to change from being the driver to one of many drivers. So harping on that a little bit, now this is baseload generation. I'll read it to you because it's a little bit hard to read, but this is a baseload generation plant. The most important thing is baseload efficiency. As we start to get into these other markets of a peaking demand or intermediate generation, we have to start stretching the capability of this plant. We do that here with part load efficiency improvements, emissions controls, advanced emissions controls. We have some technologies, clean ramp, that'll allow you to tap into those market spaces. And now combined cycles are getting stretched even further to say, I want to do renewable balancing, and how about primary frequency response and spinning reserve with my combined cycle plant? Things that combined cycle plants were never meant to do, they're being required to do now. So on a retrofit basis, we're coming up with concepts that you can come in to make your plant more usable and thus more valuable. And on a new plant basis, these features are going in that just future-proof your design. It gives you the flexibility. So that's the other buzzword that we're hearing, aside from modularity, is flexibility. I don't want to commit to how I'm going to run my plant in 3 years when I buy it, or 5 years, or 10 years. I want to be able to operate however the market is most beneficial to me to operate. So that's what we're doing. So some of the concepts, some of the technologies that we have, there's a co-start, which allows for fast gas turbine starting in combined cycle. It essentially decouples the gas turbine from the steam turbine, so you can get an unrestricted gas turbine startup. And I'm happy to go through these technologies more after this presentation or down in our booth too. But energy control, steam assist, again, concepts to reduce cost or drive down the cost of that power plant. One of them is to reduce cells of an ACC, and the other is to reduce the use of your aux boiler. Dash system and clean ramp, those both get you into that ramping stage. The dash system lets you ramp your fired combined cycle plants at a gas turbine ramp rate. The clean ramp system keeps you in emissions while you're doing this ramping up and down. So those are the different technologies attacking there. And then one of our newest one is C-Start. So that's what I'm going to talk about for a couple of slides is that's the application of a battery to a gas turbine plant, to a combined cycle plant, and some of the benefits that that'll unlock too. So if we look real quick at a battery storage into a combined cycle plant, here's one of the applications that we see for it. Again, this is time on the x-axis, and on the y-axis is plant output, so you don't have to read any of the numbers. But in this particular scenario, the grid is saying to this combined cycle plant, here is the output that I need from you on this time scale. Now, there is no combined cycle plant installed and operating right now that can do this. There is no combined cycle plant in development that can do this, that can ramp instantly by 10, 20, 30, 40 megawatts. But batteries can. Batteries can go from no load to full load in less than 1 second. 250 milliseconds, to be precise, is what we use for it. So now when you start to say, I want this ability, how do I get this with my combined cycle plant? The answer becomes, well, you can slap a battery on it. Now you can see the blue line is what your gas turbine or your power plant is doing. The green line at the bottom is what your battery's doing. So for that first segment, you're capturing that ramp rate with strictly your battery. It's ramping up and ramping down. Your gas turbine's not doing anything. Then for the second is the truly what we call a ramp rate enhancement. So you're getting an instantaneous output increase from the battery while your gas turbine or your power plant ramps up normally. And as your gas turbine or power plant ramps up, the battery tapers back out so that the grid sees that output jump instantaneous, and it shows for however long you need it, it's able to be there. Yep. How do you know what? How do you know that the grid will drop? How do you know that the grid will drop in and require that output?
Well, the first part of the graph shows that the grid demand rise
Yes.
and go down again.
Yes.
And that you will not start the gas turbine.
Yeah.
You don't know how long the period of high demand will do.
That's correct. That's absolutely correct. So, and the point of this is to show these are examples. Maybe the grid wants instantaneous output now and instantaneous output gone. That's the first hump. For the second example, it wants instantaneous output now and then it tapers down as you get to an off peak. This is not meant to be, this is what will happen on this day or this is what it's capable of. This is showing it can do this. If that first hump is 3 hours, then you'll ramp up your gas turbine and you'll just hold it there for 3 hours or however long it is. Whatever the grid is requiring, this is showing what I consider to be the extreme examples so that it'll demonstrate the capability that it can respond to however the grid needs. Does that answer your question? Okay. One other example for batteries, for a combined cycle plant, this is immediate firming capacity with a high efficiency combined cycle. So again, x-axis is time, y-axis is output. Now in this particular example, at time 0, an event happens on the grid. And an event can be anything. The loss of a major generation unit, the sun goes behind the clouds, the wind stops blowing. Whatever it is, it's requiring the grid to say, I need output from your plant right now. In this particular example, this delivers 78 megawatts in 250 milliseconds to the grid, and then delivers that 78 megawatts for as long as the grid needs it. So this was, this is one of the downsides of batteries. There is a limited time or a limited component to it where, if you have a 4-hour battery, and you need 5 hours, you can't coax it into giving you another hour. It's gone. The energy's gone. So in this particular example, with the application on a gas turbine or on a power plant, you can have that power indefinitely. So if you peel back the curtain and look what's happening inside, this is what it is. The green line is the battery, the blue line is a gas turbine, and the red line is a steam turbine. So you can see initially the green line of the battery, it's making more output than you're delivering net because it's providing black start capability to the gas turbine. Gas turbines ramp up while the battery ramps down to maintain that constant output. Then it holds, and then while the steam turbine warms up, then the battery holds and then ramps back down as the steam turbine ramps up. So outside of your power plant, beyond your fence, the grid thinks you're made 78 megawatts in 250 milliseconds, and you can make it for however long it needs it. Inside your fence, this is what's happening, and this is all inside the control system. It's not an operator having to turn two dials and match anything. This is all inside the control system for it. But the main idea here is the electrical grid sees the full output instantaneously and continuously. So that's another way to increase this value or attack other value streams. Now, speaking of the value streams, this chart shows, and again, I'll read it to you because I know you can't see the words, but this is the yellow is a conventional, what we would call a combined cycle power plant or a typical combined cycle power plant. This is what it's designed to do. That biggest component up at the 12 o'clock position is capacity or the day ahead market. That's what combined cycle plants have been designed to do. Say, hey, I want to run on this day from this time to this time at base load. So that's what it does, and it does it very well. Some of the other markets are the real-time market and renewable balancing, which is how fast can it respond, and it can, but not that well typically. So now when you look at a Siemens Flex Plant solution, with some of those concepts or those innovations that I talked about, you can expand that market. You can start to get more money for your power plant by running it slightly different ways. You don't change the capacity or the day ahead market because it's the same output in this example. But into the real-time market, renewable balancing, you can do a lot more. You can ramp much faster. You can turn down lower. You can start up faster. You can be able to start to attack those other markets. The bottom right there is energy arbitrage, which, you know, in its simplest form is you buy power, or you essentially get paid, on the battery example, you get paid to make power, and then you get paid to sell it too. But in this particular example, if power is you're on peak and you're making a lot for it, and then all of a sudden you spike down, you're in ERCOT, and the prices fall out of the bottom, how fast you can ramp down or get offline, or the minimum load you can turn down to, is just as important in how fast can you ramp back up, or what's the max load you can get to. So with our plant, you can turn down lower, you can turn down faster, so you can reduce some of those losses. And then the bottom left there is ancillary services. So this is spinning reserve, non-spinning reserve, primary frequency response. How can you get into those markets? With the Flex plant, you can start to attack those. You can do that with the fast ramping, with our dash system, with our low load turndown. You can start to do that. Now in the battery example I showed you, which is our name for it is C-Start, now you open up all of these additional markets. Again, the same ones for the capacity of the day ahead, you get more, because now you can turn your battery on while your gas turbine power plant's on, whether it's 10, 20, 30, 40 additional megawatts that you want to capture during that peak time, you can do that. Same thing with the real-time market, you can respond in less than 1 second. There's no market out there right now yet that changes prices on a second basis, but you could respond to it if it did. Renewable balancing, energy arbitrage now becomes, in West Texas, you can get paid to charge your batteries at night and then get paid to discharge them during the day. Ancillary services, obviously I talked about. Then up the left side, there's black start. So if you get paid more to have black start capability, it's inherent in the design of the battery system. And then energy storage. You can see markets, and I know you guys see it in the news, markets are requiring X megawatts of energy storage. Markets aren't paying for it yet, but that's gonna come soon. That's gonna be what drives people to start to buy these or to install these. So when it does that, when those regulations are there, you can attack those markets too. Okay, and then wrapping it all together, like I said before, there's optimized modular solutions for maximum value, whether it's our PowerCore modularized power plant system or our reduced footprint single shaft combined cycle. Flex plants, I told you how those attack those new markets or add those additional revenue streams, which, you know, everybody needs to do these days to be able to increase the successful or the profitability of your plant. And then lastly, innovations that matter. So I've showed you what we're spending money on at Siemens and some of the innovations that we're putting our time and energy into, and how we see them applying to the market space and putting more money in your pocket. Okay, any other questions at the end? We'll get to it at the end, I suppose. Thank you.
At the end. Thanks, Chris. You know how to push the button?
Yeah, I know which one to get.
Okay. I'm just going to go ahead and put this back to the general slide. Thanks, Chris. Well, we have another Chris. So Chris Corin is the project manager of 60 Hertz and integrated systems at GE Power. Our original speaker couldn't be with us today that you saw in the advanced program, so we're glad that Chris is able to join us today. Chris joined GE in 1990 as a field service engineer and spent 22 years building combined cycle and coal plants across Asia, Europe, and Africa. During that time, Chris led the construction and commissioning of numerous complex multi-unit combined cycle plants, including 5 gigawatts of F-class single shaft and 2 gigawatts of H-class single shaft combined cycle power. Chris left the field, and from 2012 and through 2016, he led GE's HA plant engineering development team as its platform manager for high-efficiency plants. During that time, he was responsible for GE's 9 HA and 7 HA single shaft and multi-shaft reference plant designs. Since 2016, Chris has been the project manager for GE's 60 Hertz plant and integrated plant systems products. He's responsible for all aspects of development and commercialization of the 60 Hertz line. Chris graduated from Clarkson University with a degree in mechanical engineering. Chris.
See if I can find the right button down here to hit. That one. All right. Yeah, so I'm going to cover GE single shaft plant configurations, the history of them, the features of them, and the units that we have out in the field today. There's two major configurations of single shaft combined cycle. One would have the generator in the middle shown on the left, the other having the steam turbine in the middle. And there's pluses and minuses to each one. With the steam turbine in the middle, it's easy to pull the generator out of the unit for maintenance and inspection. For the generator in the middle, you have a bit better efficiency on your combined cycle for a number of reasons that I'll get into later. But the lion's share of GE's single shaft combined cycle were one of these two configurations. And more recently, we've been building our single shaft combined cycles with a generator in the middle. Now, GE has been building 60 Hertz combined single shafts. As was stated earlier by the panel, they've become much more popular in North America than in recent years. GE has done a number of single shaft combined cycles, throughout the world, over 240 units going back to the late 60s. We really saw single shaft taking off in the 50 Hertz market primarily around the late 80s, early 90s. That was when gas turbines were getting big enough so that the single shaft made sense. Previously, when you looked at, say, multiple single shafts versus a multi-shaft combined cycle plant with one steam turbine, the multi-shaft combined cycle plant would have a significant efficiency advantage, about half a point of efficiency. That was because of that larger steam turbine being more efficient than a bunch of smaller steam turbines. That was one of the big reasons for it. Now, HA-class gas turbines have gotten so big that steam turbine there's not as much difference. You're on that flatter part of the curve, so to speak, of, say, size versus efficiency. So now you can have a single gas turbine, or you can have, say, two single shafts that are almost as efficient as a multi-shaft, a two-unit multi-shaft, maybe about 1/10 of a point. So now, whereas almost all of these units are in 50 Hertz, now you start seeing the later on units being 60 Hertz, single shaft being much more popular. It's still not leading the way, still not the highest percentage of units out there, but we're seeing many, many more now than we did, say, 15 years ago when the gas turbines were a lot smaller. Now, you already heard some of the pros and cons, single shaft versus multi-shaft. If you look at a one-unit gas turbine site, the single shaft is typically going to be a little cheaper than the one-by-one multi-shaft. One of the reasons we see for that is the one larger generator just being less expensive than two smaller generators, one set of electrical hardware instead of two sets of electrical hardware. Also, you have a much more compact footprint. Everything's connected together, smaller, easier to deal with, and you have the same flexibility of a multi-shaft plant as long as you have a clutch between that generator and the steam turbine so that you can have the steam turbine and the gas turbine operating independently. Now, that does have some cons, some of which aren't as applicable in, say, North America, because one of the cons on a single shaft is it's a little harder to do a phase installation where you want to run that gas turbine first and have that online first while you're still building the steam turbine. We see this more in, say, Latin America or other places where they need power quickly. They may want to do a phase installation, get the gas turbine online as soon as possible, and then keep building the steam turbine. For that, multi-shaft is a little better. It actually, it's a lot easier to execute than trying to build a single shaft in the gas turbine first. You can do it, but it has lots of complications to it. Also, although the single shaft has a smaller footprint, if you have an unusual plot plan, if you have to be creative in your location of the steam turbine, that's harder to do with a single shaft. You're pretty much locked in. But with a multi-shaft, one-by-one multi-shaft, you can move that steam turbine around if you want to, perpendicular to the gas turbine center line, parallel to the gas turbine center line, whatever fits for that particular application. And then there's some features of it. It requires more OEM integration because everything's coupled together straight up. And then for some people, that may be a plus because then you get that OEM integration. But other customers or other markets, they may want to bid out that equipment separately. So it depends on your viewpoint whether you want more or less OEM integration. This is the configuration, steam turbine in the middle, that dominated most of GE's F-class single shafts, where you have steam turbine between the gas turbine and the generator. This is a really simple arrangement. You only have one thrust bearing. That's in the gas turbine. That carries the full thrust load of the train. Steam turbine transmits torque from the gas turbine down to the generator. Now, this is also easier, as I was saying before, for the generator maintenance. You just pull that generator field out the end of the generator when you want to take the unit apart. However, it does drive some problems as well. If you have an indoor arrangement, then you have to have room inside the building to take that field out. So it makes for a larger installation potentially. Also, with regard to efficiency, since your thrust bearing is in that gas turbine, and then you have axial expansion from that thrust bearing all the way back to the generator through that steam turbine rotor, you're going to have to leave some pretty big axial clearances to, when you're cold, to try to make sure that you have good clearances when you're hot. And those clearances also, say at part load, they're going to impact your efficiency because you have so much expansion for that thrust bearing because you have only that one thrust bearing. Now, this is the configuration that GE did with some of their later F classes, particularly in Europe, what we called at the time the 9FB, which had the gas turbine on the end of the generator, the generator in the middle, steam turbine on the end of it. And that solved the issue of the long axial expansion of from the thrust bearing, because now the steam turbine can have its own thrust bearing because it has a flex coupling in between the steam turbine and the generator itself. Now, one problem that this causes is having the generator in the middle. Now you have to move the generator or find some way so it can pull that long field out of the generator internal so you can do maintenance on it. But this also allowed us, excuse me, with the axial exhaust steam turbine, you just put a condenser on the end of the building. You can have a very low center line, low cost of construction. It solved some of the problems that we had with the steam turbine in the middle, but it also had some issues with it as well. On our earlier designs, we did not have a clutch between our steam turbine and our generator, and we had this flex coupling, so whenever you started the gas turbine, the steam turbine was always along for the ride. And when you're up at synchronous speed and you don't have any steam going through the steam turbine for power generation, you're going to start getting windage heating on your last stage buckets. And because the potential of this heating could damage the buckets, we have to put a little bit of cooling steam through to take that heat away, basically. Well, that requires a larger aux boiler. That's cost. That's more CapEx, more capital expenditure on the power plant. So with our latest HA single shaft combined cycles, we left the generator in the middle, but now we've gone to a clutch in between the steam turbine and the generator. That allows us to start the gas turbine independent of the steam turbine completely. We can still use the generator as a starting means for the gas turbine, but we would clutch out the steam turbine and only bring it online later when we have steam available from the HRSG. So installing the clutch allowed us to move away from a larger aux boiler, downsize that aux boiler. That helps with your air permitting on sites. It also reduces your total, your total capital expenditure. Now, to solve the issue of access to the generator for maintenance, and this was actually developed on our launch 9HA single shaft in Bouchon, France. We develop a system where we can move the entire generator stator to the side for maintenance. Jack the generator up, put these red rails underneath, and then with hydraulic jacks, just push it off to the side. We built this tooling, tested it for the first time during the construction of our plant in Bouchon, France. Went very well, and now we have this hardware if a customer has to go in, look at the field, it's a much easier way to do it. And much less expensive than trying to use, say, very heavy-duty building cranes to move the generator out itself. Because if you try to do that with heavy-duty building cranes, then you have to have, say, 200-ton cranes. You have to have a building structure that can support it. That drives cost. This is a very, very cost-effective solution for us. And we heard a little bit already about modularization. That's something that GE's also worked on extensively. For our, starting with our 7HA gas turbines and now our 9HA gas turbines, all our gas turbine accessories are modularized in what we call our prime packaging configuration. This significantly reduces the amount of labor and commissioning that needs to be done on the gas turbine after it arrives at site, taking out approximately 1/3 of the labor needed to build the gas turbine. Now, we've extended that in markets where we offer, say, a turnkey construction, which we don't really do in the United States, but in markets where we do offer a turnkey construction, this is how we execute our installations, modularizing the hardware, building it in the shop, taking it away from the weather, taking it away from the site issues, doing it in a shop, and then bringing it to site. Approximately 8 plants are where we've done this at over the years. A lot of them executed with the former Alstom group that we brought into GE, including a plant in Conil, Germany, 24 months from notice to proceed to COD in a brownfield site, and a very tight installation using modularization. Also, this is the general configuration of our 9HA01 site, our launch facility, our launch project with Electricity de France in Bouchon, where we set our world record for efficiency at 62.22%, and also have hot start times of 22 minutes from pushing the button to base load operation. So high efficiency, also highly flexible in this configuration. And that's one big thing about looking at a multi-shaft and as opposed to multiple single shafts on a particular site. If you have a multi-shaft combined cycle, then you have, excuse me, say a 2x1 or a 3x1 multi-shaft combined cycle. You have a single point failure on that plant, which is that steam turbine and that steam turbine generator, and then the electrical hardware for that steam turbine generator. If you have a failure on any one of those pieces of equipment, you're probably not going to run the gas turbines in simple cycle. So there's places where that whole plant can be taken out due to a single point failure. With a multiple single shaft configuration, if you have a failure on one of your gas turbines or one of your steam turbines or one of your generators, everything's fine. I mean, not everything's fine, but you'll still be producing power with the other single shaft at base load efficiencies. If you have a multi-shaft and one of your gas turbine goes down, now your steam turbine's running at half load, running at part load efficiency. Your other gas turbine's still fine, but your combined cycle efficiency is going to be impacted because you're at part load. With a single shaft, one of those units goes down for any reason, the other is still at base load efficiency. So that's another flexibility advantage of the single shafts when you look at a combination of single shafts on a particular site. And as was mentioned before, gas turbines are just getting bigger and bigger and bigger. And in 50 hertz, they've been bigger. They've been in the 400 to 400 megawatts, 500 megawatt range on a single shaft for a while. We have just gotten there, so to speak, in the last few years with the H class as we know it today. You can see how big they are in the 50 hertz world now, pushing over 800 megawatts for a single shaft combined cycle. And on the 60 hertz, we're looking at pushing up to, getting closer to the 600 megawatt range for one gas turbine, one steam turbine, and one generator. So that combination of flexibility and also, in a lot of ways, the reliability too, to be able to produce base load power, that is a very big advantage of the single shaft, in my opinion. Thank you. That's all I have for today. Do you any questions, me specifically, before we sit down and and go to the next speaker?
We'll give him a chance in a minute.
Thank you. You said.
Gotta get you're the only one that knows the key to bring us back. Thanks. Okay, let me get Mitch up here. Thank you, Chris. Okay, so we're going to shift gears a little bit, and we're going to talk, we're lucky to have an owner and a constructor here today. And, an owner that is responsible for construction. So this is the fellow that gets to live with all of these wonderful ideas. Mitch Garber is the Vice President of Project Management for Caithness Energy. Mitch has joined Caithness in 2005. He leads the company's efforts in construction, engineering, and permitting of power projects. Prior to joining Caithness, Mitch worked as a project manager for Skanska USA, a large construction company that is in the construction of power plant business. Earlier in his career, Mitch spent 10 years at Cogen Technologies, where he was increasingly responsible for engineering, plant management, and project management. He began his career as in operations and engineering at Consolidated Edison in New York, and he holds a BSME from State University of New York at Buffalo. Mitch.
Thanks, Jeff. Everybody hear me okay? Okay. So I just prepared a few slides on Caithness. We sometimes tell people we're the biggest power company nobody's ever heard of. We like that, actually. And then I wanted to listen to what my colleagues from the OEMs had to say and just react, and maybe that'll get us going a little bit on the question and answer at the end. Because my sense is that most of the folks in the audience are more in my side of the business. We're a user of these products and a deployer of these products as opposed to a developer of these products. So Caithness has been around a very long time. We've been involved in 43 power projects, over 3,500 megawatts of gas turbines, 2,000 megawatts of wind. You could read the numbers. We really started as old school IPP, chasing PPAs, chasing standard offer contracts in the 80s. We evolved into big renewable company, and then into thermal. So we've been at this a very long time with kind of an old school private IPP mindset. I think we're probably the last of our peer group, right? Mikowski is gone, and the Roys are out of the business. Ellis Power is still around, but those are the kind of folks that we consider our peers. So right now, operating projects and things in construction. Just some highlights. Caithness Shepherd's Flats, 845 megawatt wind project in north central Oregon. It's the first North American deployment of General Electric's 2.5 megawatt turbines. Went online in August of 2012. It's about a $2 billion project, financed very successfully using a combination of debt, equity, and United States Department of Energy loan guarantee. The next operating project is actually the one on the bottom, Caithness Long Island. It's a 350 megawatt Siemens project. It started life being based on what we then called the Siemens 501 FD3. It's been upgraded a couple of times. So it's really running top-of-the-class F technology from Chris's group. Good project. That was a turnkey solution from Siemens that worked well for us in that business environment. It's a long-term power purchase agreement with the Long Island Power Authority. It's currently running over 99% availability. It supplies over 11% of the electrons that are consumed on Long Island. And when you look at where the power comes from between on-island and off-island through cable connections, we're generating 21% of the power generated on Long Island. And then our current adventure is the Cape Nismoxie Freedom Project. It's a project we took over in late-stage development from another developer. We're about 88% complete with construction. Gemma Power Systems is doing the construction for us. It's in northeast Pennsylvania. And I think it fits this panel very well. It's 2 single-shaft, 7 HA.02 machines. We bought Power Island scope of supply from General Electric, and Gemma is doing the balance of plant and the installation. And then we have a bunch of other stuff in development. Caithness Beaver Creek is a combination of 4 80-megawatt wind projects in Montana. And then we have 3 projects that are all looking at various numbers of single-shaft machines. The Guernsey Power Station in Ohio, the Tioga Power Project, where we're partnered with Energy Solutions, and the Harrison Power Project, where we're also partnered with Energy Solutions. Those 2 projects are slated to be single train, single shaft one-on-ones. And then we have Caithness, Long Island. We have an expansion opportunity there that we've been working on for a while. So, you know, what do we hear from the OEMs today? What's important to us as owners? This is gonna be really surprising to you guys, right? We need it cheap, we need it fast, and we need it to work. I mean, it's really just that simple. And I think, you know, what is cheap, what is fast, and what does it mean for it to work is, I think, what these guys have been talking about and focusing on it. And I think as a customer, and I've not always said that, I think the manufacturing community is being responsive to a certain extent to what we need as developers, but they're also, I still think, maybe missing the trees for the forest, you know, to a certain extent. You know, what does it mean to capture? What are the key components of value for a particular project? And they really vary from place to place. The key components of value, if you're building an ERCOT, are vastly different than if you're building in the Marcellus Shale in PJM. I know a lot about the second and not very much about the first. ERCOT's not a market that we focus on. We spend a lot of time doing PPA-based projects for Southern California Edison and for Pacific Gas and Electric. Those are very different value propositions than, pick another kind of a project. So I think it's important that these machines be able to do a lot of things. So I appreciated the comments that Chris made about stretching out that operating band and not focusing very much or as much on just that one baseload piece. From our perspective, we're absolutely, these guys are preaching to the converted on single shaft versus multi-shaft. And I think it works even up to 3 machines on a site or maybe more. We really like the fact that we can standardize on our design. We're working on a reference box. No matter where we put this power plant, we can do a vast majority of the power island standardized from one place to the next. It's very important to us. The size of the unit, again, I don't think of these plants as a gigawatt power plant or a 1,500 megawatt power plant. It's a collection of 500 megawatt blocks, which I still think are very manageable blocks in the grid, especially when you're talking about lower turndowns that these guys are providing and the fast start capabilities. So I think there's a lot of really good stuff. I think some of the issues that I struggle with from the OEMs is it's good to look to provide more parts of the value chain and to anticipate what the market needs. But I also think, and this is another point that was made, Chris from GE made, you have to, sticking to your knitting is also important, what you do well. And I get really nervous when I sit in these presentations all the time, the power plant in a box concept. And there's a lot of value that's added at other parts of the chain by folks that work for Zachary and folks that work for Gemma and other places. And I get nervous in the rush to provide value to the market that the OEMs are providing, that they're trying to do things that they don't necessarily do as well as others do. And then the product becomes very rigid and you lose some of that flexibility. So I think our job as a developer and as a owner project management team is to, the DOR in that contract is really, really important. Who's doing what, and are we getting the best value from the different suppliers that are available to us, that are all out there. But I do think that all three manufacturers are doing a better job finding products that have the flexibility, that fit what we need to do. It's near and dear to my heart. I'm going to give you just one anecdote, and then, Jeff, I'll turn it back, and you can take back over the session. We built Caithness, Long Island, came online in 2009. Just before we went to commercial operation, we had a meeting with the New York Independent System Operator and the utility. And they said, here, you have to fill out this form and say what services you're going to provide, what markets you're going to participate in now that you've built this great new plant. So we said, okay, capacity, yep, we can do that. Energy, okay, we can do that. Spin, yeah, we can do that. Regulation, yeah, we can do that. And went down the list, and we gave it, and the ISO said, well, you made a mistake. I said, what do you mean? He goes, well, you can't do regulation with a combined cycle plant. I said, why not? I said, I had Siemens give me a place where I can take your AGC signal, plug it into the control system, and it'll move the unit up and down. So what's the difference if my operator is telling it to go to 180 megawatts or you're telling it to go to 180 megawatts? I can do that. And they're like, well, nobody's ever done that before. Okay, great. You know? So I think that having the OEMs think about these things the way that we've been thinking about them as operators trying to maximize value for a long time is encouraging, as opposed to here's my product, you know, go do what you want with it. So with that, Jeff, I'll turn it back.
Thanks, Mitch. Well, we have a few questions. The first one we're going to take is the gentleman over here who brought up the question earlier, and I'm going to try to paraphrase it and see if I get this right. And if not, I'll ask you to fill in the gaps. So the question was, could you provide us some information about the heat rates on J and as opposed to H class combined cycles? Was that pretty much? Pretty close, yeah. Pretty close. You want to go back to F's too? No, okay. Anyway, so let's go ahead and go down the panel, and to the extent each one of them can say anything. Of course, they may also all tell you, come see me up here in a minute, or come to my booth. But we'll see. I don't know. I'll tell you what, we'll start with you, David, this time. Next time we'll go the other direction. So.
Okay, can you hear me right here? This is a different mic. It's a little bit quieter or weaker from what I've heard. Basically, right now in industry, our J and the HA are playing a game of leapfrog or neck and neck or on top of each other for the most part. I assume that's the H you're talking about, or the HL also.
Well, my question was, really, I mean, I'm familiar with some of the classes, right? And there's a lot of terminology that gets kind of thrown around, right? H and G, and you know, from the F to the G, we went to some kind of technology upgrades, some pooling of blades and that sort of thing. My question, and there was some heat rate benefits because you could kind of pop the firing temperature a bit when you did that. But really, my question was maybe it's more naive, and maybe we're making it a little more complicated than it needs to be. I was just wondering, when we went to the H technology, is there something different between the G and the H, and is there a heat rate gain because of that, and how that happened? That's really kind of the crux of my question.
Okay, I'll talk more on the J since that's our equipment and that's what I know. The H I kind of just guess at. But like I said, the J's and the H's are kind of close to each other. Running up the temperature, the working fluid inside the gas turbine, like I mentioned, the pressure goes up to keep that exhaust temperature within line for the HRSG on the back end. Materials change or cooling strategies change. We introduce typically steam cooling first so we can keep the combustion or we can keep the air for combustion or keep more air in combustion. And then once we learn how to cool better with air, we then go ahead and replace the steam with the air. On our J machine, in order to keep the lower temperature materials, we've incorporated this enhanced cooling system. which is a simple, I mean, there's discussions. Is it a blower? Is it a pump? Is it a compressor? It's only 30%, so it doesn't do a lot of extra work, but it does give us the air to cool the component and yet use that heat it picks up back in the gas turbine again. So first laws of thermodynamics, temperature is what matters, so we can drive temperatures higher with better airfoils and seals and such to take advantage of that to get more power out of the gas turbine. You'd have enough energy going in the bottoming cycle to keep it running as efficient as possible. So the overall driving is just basically getting the turbine inlet temperature up and keeping everything running and maximizing, seal flows, tip flows, leakages, and so on throughout the gas turbine. The enhanced cooling system we have, like I said, is a 30% bump in pressure. It's a simple cooler system that takes the heat and puts that in the bottoming cycle, so we're recuperating there also. Not a lot of technology in there that's new or wild. It's all over petrochemical plants. And even our IGCCs have a similar system, so it's very robust technology.
Did you have I think he's actually kind of looking for a number, too. Or a range of numbers.
I mean, my feet are getting...
You mean between 1 and 100?
You mean my feet are getting kind of warm here, Jeff.
Oh, okay.
As Paul mentioned, I mean...
Gas turbine world kind of.
Yeah.
Whenever it comes out. Right now, the gas turbine we're looking at for the JAC range is in the 44% LHV, 64% in combined cycle. There's always little tweaks that are happening as gas turbines evolve, so the numbers are always reaching up, and then a new frame comes out that just takes a step. But right now, for the combined cycle, we're doing 575 combined cycle of 64%. Back in 2004, Mitsubishi targeted 65% efficiency in combined cycle, so we're very soon to be there. Even Paul mentioned in his keynotes that.
Yeah, I was gonna say in the keynote presentation, he said 65%.
Yeah, we're building that plant now to be getting there. So we're going to test it before we sell it to make sure we're there when that happens.
Thank you.
You're welcome.
Lucky Chris from Siemens.
My answer's a lot easier now that David talked through all of that. Firing temperature and cooling are the primary drivers for it. We have some other technologies like our HCO system, which is our hydraulic clearance optimization, which it physically moves the turbine blades away to increase the range or the delta, the gap between the casing and the blade, so that you can do hot starts or anything like that. But then as it gets to baseload operation, it shifts forward to reduce that gap and reduce the amount of airflow that bypasses it, which increases the efficiency too. So outside of those technologies, it's components and it's cooling frames as well. And like David said, like everybody's saying now, it's a race to 65%. But our F classes are consistently, 58 to 61% efficiency, and our H and our HL is north of 63 on a net basis. So I'd say we're pretty much on par. We're neck and neck with. You're going to hear the same thing from all the OEMs, and it's just, can you balance out the higher firing temperature and increase the cooling without using too much air that you're taking it away from the efficiency of the plant?
Chris from GE.
Well, right now, GE's just released our 2018 product catalog, and right in our catalog, we're stating 64% for primarily in the 50 hertz markets, where the machine being a little bigger gives you a little bit more advantage on the efficiency, but we're capable of 64% right now. And on 60 hertz, it's more, say, in the high 63% in that area, but a little different approach on our side. We went hard on steam cooling back in the day, back in 2000. In fact, part of my career in the field was putting in all the steam-cooled 9Hs that we put in the UK and also in Japan. That was a very complex machine, very well functioning, but long maintenance outages due to the complexity, high cost for the plant. So when we went to the next generation, the HA, we want to make it as simple as possible. The air-cooled gas turbine. We don't require any off-base cooling systems. We don't require any other, say, active systems for clearance control. We have a second inner shell inside our gas turbine that moves with the hot gas path. As the hot gas path heats up, the shell heats up and keeps the clearances the same. As it cools down, it also keeps them the same. So no active systems to manage this. And we also use the same alloys in our hot gas path that we developed in our F class. We haven't developed any new super alloys, any new hardware. We hit these higher firing temperatures with better, or we withstand these higher firing temperatures with better thermal barrier coatings, and also and better management of cooling flows, just like everyone else is trying to do. You know, I gotta say, I think we've done it a little simpler.
Okay, I'm going to take questions from the audience. I've got another one here in a minute, but let everybody have a chance. So, there we go. Please. Oh, would you mind telling us your name and your company, please, if you don't mind?
My name is Sandeep Goswami. I work with Mitsubishi Hitachi. This question is for Chris from Siemens. What's the difference between the power block scope that you mentioned, or the power core scope that you mentioned, and the power island scope? Scope difference.
I'm going to give you the easy answer. It depends. And the reason that it depends is a power island is, I would say defined, but then it's different every time. But the components are essentially the same. With the power core concept, it's a high modularization of a list of, right now there's 89 different systems that we can modularize. You don't need all 89 systems. So the scope is, okay, we need one of these and one of these, and for this case it makes sense to modularize this, or it doesn't. Our pipe rack can be modularized to this extent based on this layout. So it's I would say that it's a scope offering, but it's highly customizable inside. Is what blocks do you want to put together? What building blocks, what Legos do you want to make this final power plant? And all of those blocks are done on a component level.
So do you, the subsequent question is, do you offer that as an option to the customer, that do you want a highly modularized solution, or do you want the power island which is not highly modularized? And it depends what you're looking for.
We don't ever say that. We don't ever say we'll give you something that's not highly optimized or modularized. But yes, I mean, to be honest with you, the way modularization started to come into the industry was places where labor was either impossible or incredibly expensive, right? Because then it was, the trade-off was, okay, I'll save the dollars there and I'll pay more dollars on the shop side, or the dollars ended out to be the same. It's just, where do you spend them? Do you spend them over here, or do you spend them over here to be able to get to that bottom line? But now we'll offer it if it makes sense for the project, because to be honest with you, some cases it doesn't make sense. If this is a crazy layout where things are all over the place and the field labor's dirt cheap and it's in, it's on the equator where it's sunny every day, then hey, maybe it doesn't make sense. But to be honest with you, if a power island makes sense, there's some level of a power core modularization that's going to make sense, whether it's a half a dozen skids or auxiliary systems or the pipe rack, whatever it is. So we actively look at it and say, does this make sense or doesn't it?
Okay, so you basically maintain multiple designs for the same component, depending on what kind of modularization the customer is looking for.
We maintain the flexibility to change the design of them for each application. That's right.
Fair enough, thanks.
You bet.
I'll ask Chris or David if you want to add anything to that. Nope. Or,
I'll just add that, as I think all the OEMs, we can offer equipment-only scope, power island scope, turnkey scope. It all the market, the customer, the EPC market, that's what matters with regard to where GE can add value to the customer, to that project. If we can add value by providing more scope and more engineering where there isn't a strong EPC base, we'll do it. If it's our gas turbine in certain applications that the customer wants specifically, we'll do that, and we'll do anything in between.
okay, I'm going to add two questions on that. First off is, I guess I would kind of call it pull-through, and that is from entire product lines. I know that this was a push kind of in the industry more in the last 5 years, and it's more along the idea of power islands have been around a long time. But I know particularly with GE, with the acquisition of Alstom, that you had more of a corporate mandate to try to pull through more material through the process. I guess my question is, one is if you want to comment on that. But the second thing, if as an owner and an IPP, does that give me any better reps and warranties? Does it give me any better, LD protection or something like that? I'll ask all three of you if you want to comment on that. So I'll start with Chris. And remember, they are videoing it, so you may need to talk a little bit. Pull the mic a little closer. You don't need to move closer, just pull the mic closer. So, yeah.
Sure.
Yeah.
You know, prior to the acquisition of Alstom, GE was the largest purchaser of HRSGs in the world, because we'd purchase an HRSG from a supplier and wrap it in our package. However, the acquisition of Alstom and getting the HRSGs was more to pull that in-house, not so much to a pull-through of hardware for any particular customer, but because being able to wrap it all together, in our opinion, adds a lot of value. Because if a customer, you know, there's pros and cons to bidding all the equipment separately. Customer may be able to get a better deal by putting everything up for bid separately, but doing that, not having it all wrapped together by the OEM, you end up with the HRSG supplier, the steam turbine supplier, the gas turbine supplier, all with some margin on their performance, on their bid, that then the EPC would wrap, potentially have some margin to as well. By us providing the whole package, there's only one margin on the whole performance calculation, and we think that offers a lot of value for the customer.
Good. I appreciate that. Chris, you want to say something? Yeah.
Yep. That's a good point, too. And to be honest, I'd be lying if I didn't say that there's a loose corporate mantra to sell as much Siemens gear as you can for every project, right? That's always the message that there is. The more scope we have, the better. But to Chris's point, it is true that we, as Siemens, we can't control things that we don't provide. So if you get into the point where you're trying to balance or optimize things and it's looking to, hey, performance guarantee-wise, where does this go? There's got to be clear lines of, hey, that wasn't our scope. That's not what's supplied. Some customers like to deal with that and some don't. Some want the one neck to choke approach, and it's, I want everything to come from the same place so I know there's one phone number that I will dial if this doesn't work, and no matter what it is, that person is responsible for it. So there's that aspect to it too. But honestly, to be completely frank, the way that the market is right now, it's not a matter of how much Siemens equipment can we get in this, it's how do we win this project. There are not a lot of projects out there to be had. I think that's constant across this panel that you're here, that business is not great right now. So we have to take the approach of what's best at the end of the day for the customer. And whether the customer is an end user or an EPC, we would go into an EPC and say, hey, we have an idea for this of PowerCore. And initially the EPCs say, well, you're just taking our scope. That's what we do. But when we get to the point of, okay, this makes more sense because if we don't do this, we may lose the project. So let's do this, let's work together, let's partner, whether it's with the customer, with an EPC or another vendor. How do we make a more competitive offer altogether? Because like I said, there's just not a lot of projects to be had out there, so we've got to attack each one as competitively as we can.
As far as like the pull-through mentioned, power islands are nice and yeah, a lot of equipment. We would like to sell as much as possible also. And single shafts kind of do drive that also, because it's always hard to tell when you have one set of terminals what's the gas turbine megawatt versus the steam turbine megawatt. So that's why you want to have the OEM wrap that whole entire chain, just because that's one person responsible for that thermal block or the whole plant also or included. You wouldn't be bidding anything out. I guess that's about it. And I mean, IBIDed for everybody else too.
Yep. Mitch has a question, comment.
Yeah, I think there's a real tension when you put these projects together. When you start, as I said earlier, I think the DOR is one of the most important documents in a contract. The thermal performance, 100%. You get the HRSG, you get the critical pumps, you get maybe an air-cooled condenser or a surface condenser. The more scope you get into one place, the more it could be looked at holistically and margin taken out of places from a performance point of view. But the guys that are doing that, the guys that are running, ProMod or well, ProMod's not, used to be Gate Cycle, who are running heat balances are not necessarily the guys who really know how to build these things. And we think it's very important that you really define physical scope of supply to go along, with where are we getting those performance components from, so that when you get to the field, it's actually coming the way that it's expected to come by the EPC, whether that's whether that's between two members of a consortium or whether the owner is sitting in between. It doesn't matter. And with international sourcing of components, with cost structures changing all the time, it's very, very important to nail down, what do you mean by constructability? How big are these boxes coming? And if you have a non-traditional supplier supplying a piece of equipment, if I'm buying a pump from General Electric that I don't typically buy from them, I have to watch how they buy it. Because I might know KSB better than they do. So I have to understand what's their spec, where's the margin, is there enough margin, how's it gonna get installed, how's it gonna come off of the truck, and how's it gonna wrap it into the power plant. So I think there are a lot of challenges based on how you choose to ask an OEM to quote your power plant. And I think you have to be an involved owner team, regardless of what your delivery method is, to get that right and to get the advantages that there are. There are advantages to doing that way, but you have to go get them. They're not just gonna show up.
Mitch, could I ask you maybe to comment a little bit more about maybe more of a historic trend of back, say, 10 years ago when, or maybe even up to 15 years ago in the F-class world when we were doing 201s and everything was bid out. I'm kind of thinking like the days of Calpine Construct and stuff where they were, buying a fleet of gas turbines and a fleet of steam turbines and they were parsing them all together. And really where I'm going with this is kind of the margins they probably had to put in their pro forma for, to just cover, performance errors and stuff versus what you can achieve now with this total integrated single shaft concept here,
Yeah, I mean, that's a whole nother panel, right? But
Sorry.
no, I think it's important. The suppliers need to have to understand what's the mentality of the customer. And the business went through a cycle, through the bubble, around the turn of the century, where that was a long time, right? It didn't
was a
seem like
long
it was that
time
long
ago,
ago,
yeah.
did it? So, where you had companies like Calpine, like NRG, like FPL Energy, that had large staffs of engineers that were pulling from an old utility mindset that said, well, why am I going to pay General Electric, extra margin to do all of that stuff? Just give me what I want. We'll bid it tight, and I'll buy the next piece, and we'll bid it tight, and I'll buy the next piece, and we'll bid it tight, and we'll put it all together. I've not worked for a company like that. I tend to look a little bit more holistically, and what's my overall performance guarantee? What's standing behind it? Can I finance it? Can I convince the independent engineer I don't need any more margin on top of that because I got it put together tight? And as engineers, we hope you get to the same place. As business people, we know that you don't necessarily. So I believe that these projects work best when you assign those risks to the people that are best able to deal with them. And I think that as you've gone through cycles of the business, and we've seen, unfortunately, what's happened to some great companies that have been in our business, that a lot of times when you're chasing that last dollar, you end up taking risks that you're not best suited to deal with.
Right.
So I think, in one way, shape, or form, that kind of fully wrapped project finance model, I think ultimately ends up to an optimized solution if you buy it outright.
Next question from the audience? Yep, please. Name and,
John Gillette, backup. These questions are too softball.
well, ask us a hard one.
I realize I'm asking it out of curiosity, not because I'm mean, which I am. It's for the gentleman from Caitlis, and you may not answer it, but so your Moxie, what was the name of the power plant?
Freedom.
Moxie Freedom is using one of the latest technologies, right? How close is your performance guarantee to the number advertised in gas turbine world handbook? And I don't want numbers. Is it too close? Somewhat close? Not even in the neighborhood?
I actually have no idea because I don't pay a whole lot of attention to what's in gas turbine world.
That's answer enough. Let me give you some representative numbers from a power plant. I'm not going to name the OEM here. The power plant is less than a year old. It's a gas turbine combined cycle power plant in PGI. November 21st around noon. Give me a guess about its LHV efficiency, combined cycle.
I only do HHV, so it should be 6,300, 6,400, I don't know.
Anybody in the audience? Efficiency, I said.
Oh, efficiency, oh, sorry.
Lower heating value
Yeah.
efficiency.
Oh,
A power plant in PJM, not even 1 year old.
Hmm.
And nothing's wrong with it.
and nothing's wrong with it.
Is ACC or cooling tower?
54.5.
How much was the number?
54.5.
Wow.
So I think this 65%
Mm-hmm.
shenanigans are going too far.
Mm.
Don't insult our intelligence.
Mm-hmm.
And I can give you numbers about the world record holding power plants too. And don't get me wrong, these are beautiful. I was in Irshing, the best power plant I have ever seen. I was in Bouchain, right up there. Efficiencies, much better than 54.5. But nowhere near.
May I just make a comment?
Yeah, please make a comment. This is your chance.
Good luck. I think this goes to part of what was mentioned here too, as far as that point, that optimized point. That's a wonderful day.
Absolutely.
Is the value. I don't mean this defensively. I mean this just it is, because 10 years ago when I was doing some testing at one of our latest G machines at the time, our guarantee was X, but we did the testing. We showed out and we proved it and we worked it through, and then we're going on to the next block of machines. And I was just out of curiosity, 8 months, 9 months, a year later or whatever, look back to see how they were operating that plant. If it was like we would operate it to do the guarantees and stuff. They had all kinds of redundancy going on, which was just eating into those numbers. But that's the way that owner wanted to run it, to make sure they had no problems and no issues as far as a failure and dropping. So,
Absolutely right, and Chris was very much right.
yeah, so as far as
One number is not important.
it depends on how you run it.
That brings me to another question. I think the bottoming cycles that are being at least built or advertised for these very super efficient gas turbines are overblown. I mean, with a 7HA.02 or J-class machine, I can build a one pressure reheat fire bottoming cycle and get very good efficiency over the load range, and it would be damn cheap. Any views from you?
That's actually something that we look at with our customers. What's the economic value? Is it 2 pressure reheats, a 3 pressure reheat? And we're not going to force anything on a customer that they don't want. It's whatever works best with their economic model. And at this, all the evaluations that have been coming out, at least North America, on the HA class machines at the 3 pressure reheats are coming out. Now, what I will say, you mentioned the plant in France. I think we need to be careful when we look at these high efficiencies. What bottoming cycle cost are we talking about? Because if you're talking about, 600C and higher on temperatures, 2,700 PSI on your steam pressures, that's getting very expensive on your HRSG, getting on your steam piping and on your steam turbine. The plant in Bouchain, where we set the world record, 1065F and 2,400 PSI.
Talk about heat rejection system also.
Yeah, cooling tower and whatnot.
Natural trap cooling tower. And anyway, I don't want to go into detail.
No, but I want to comment though, as the is more of a developer guy. I think the thing, because this is the life I've lived for a long time, like y'all guys. There are sensitivities that are run, and so you tell me I've got $3 Marcellus gas, and yeah, single pressure may be the way to go. But what if you have 475 Marcellus gas in 10 years?
Up to 6.
Yeah.
With the calculations, 2 pressure reheat
Mm-hmm.
is resistant until $6, $7.
Till $6 or $7, yeah.
You don't need them.
Yeah.
Especially the way power plants are built and run in the United States. Nobody needs
Well, where I,
deeper 3 pressure reheat, damn expensive. Okay, in some place, if you are paying $15 for the natural gas,
my,
and if you need your power plant, I mean, round the clock, that's another story.
yeah, but no one's paying $15 for gas, even at Tokyo Harbor. It's only $9 today. Yeah. So, but I do agree with you one thing on, and as being in this industry for 40 years and watching the evolution of just thermal stations, they always start out base load, and then they end up more and more cycling and Eventually, the life of a power plant is it ends up as a peaker and then it gets retired. You know, I mean,
I've got combined cycle power plants are not running.
yeah. Well,
Just sit there.
I totally agree. And of course, just an interesting little bizarre fact. So Saturday in ERCOT, 24-hour, round the clock power price, $18 a megawatt hour. $18 megawatt hour, $3 gas. Tells me the heat rate's 6,000, and that's before you spend any money on variable O&M. And it's a different world when you have merchants and wind, but enough on that.
Can I add some, I
Yeah,
just
yeah.
want to add that
Mhm.
the two 7HA.02 plants, 2-on-1s that we have in ERCOT,
Yeah.
these are the first two 7HA.02s,
Mhm.
they are running 95% of the time in ERCOT. They're doing load following, and they're running north of 61% efficiency with an ACC.
I was there.
So was I.
Yeah. No, the beauty is the turn down that they have.
Not even close.
And how low will what's a modern turn down ratio on a HA.02? Dot,
25% staying in emissions compliance. We can do lower in special situations, but what we advertise is 25% to 100% and ramping 50 megawatts per minute or 60 megawatts per minute.
yeah. Drastic difference than the 17-year-old version that only goes down to 60% load. Question in the back, please?
Actually,
wait,
can I
one
respond to
sec.
that real quick?
Yeah.
Because I actually read a Bechtel paper on three-pressure reheat, and is it worth it? I don't know if you wrote it, or did you write it? It was a great paper, so nice job. But I guess you don't need to hear that from me. But anyways, just to respond to your point, I think, and I think that this is unfortunate, and you're in the position of Bechtel or EPC, which is commonly in the middle, right? You're not the end user for it, and you're not the OEM supplier for it. And where we get pushed, and when I say we, I just mean Siemens, I imagine it's the same for you guys, but a lot of times we'll do our technical analysis and we'll say a 3-pressure reheat is not worth it on this project. This should be a 2-pressure non-reheat. That is all that they need. And you'll talk to the operator, he'll say that's all that I need. The problem is they are requiring, well, no, we want a 3-pressure reheat. We're buying a new combined cycle plant. Why would we want to sacrifice any efficiency? So we're driven a lot of times by customers who say, I want the maximum efficiency you can give me. And even if we go to them and we show, look, a 2-pressure reheat or non-reheat makes sense for this, and look at the economics of this, it's, I want the most efficiency you can get. Feel free to put that in, and let's compare it to Mitsubishi's and GE's 3-pressure reheat and see who wins out in the efficiency battle. But I agree with you completely, and we do that analysis. I know at Siemens, and I imagine you guys do it too. And I agree with you wholeheartedly that 3-pressure reheat is rarely the right way to go.
And the reason for that is customers don't know what they are doing, and whoever running those performance.
I didn't say that.
Well, I said that. When I was in GE, I have heard customers asking for 1100 degree steam temperature with a gas turbine whose exhaust temperature was like 1120 or something like that. Said, why? No, because it's a technology.
Yep.
And those proformas are done such Mickey Mouse way. That's why they come up with these expensive bottoming cycles. Nobody needs them, they cost a lot of.
Yeah.
I'll-
It's good to know, at least you are being pushed too. I mean.
I'll defend us little developers from one perspective, and it's a little funny story. So if you think about this, like ERCOT, if you have a 15-minute market interval, and the world's always changing around me, that means I can only get a 10-minute loan because I don't know what the next interval's going to be. So, anyway, that's what we say as merchant world in ERCOT. Question in the back, please. Yes, you. Yeah.
Hi, Garrett Goldfinger from Power Engineers. Just had a question back to the whole single shaft, multi-shaft discussion. We still see a trend with large regulated utilities going towards multi-shaft units, while we find developers are going towards these typical like 500 megawatt blocks that you can replicate going across. What do you think the driver for that is, on that end? For example, Dominion has a 1600 megawatt plant that they're building right now that's 300 watt. Why didn't they go with this?
My opinion on that is, with a 2-on-1 multi-shaft, it's a little cheaper to build than 2 single shafts. You have one big steam turbine rather than 2 smaller steam turbines. There's a cost differential there, so there's a little bit of a cost benefit on, say, 2x1 versus 2 single shafts. It's also going to be a little more efficient too because of the larger steam turbines. So you got a little better efficiency. So if you have a customer that's going to run significant amount of their time at base load, such as a regulated utility, they're going to run their most efficient assets first. Then it makes more sense for them to run a big multi-shaft that they're going to run more often than not. Now, if you have someone that it's more flexible in operation, where they're not going to be running base load for a long period of time or for an extended number of years, then the single shafts, in my opinion, that's why we see them on some of the non-regulated marketplace.
Let me take a shot at that. I think that, and to the other gentleman's point, I think your view of the market that you're working in drives your decisions of what to specify to a contractor and a supplier. And I think if you're looking at a regulated utility in a market that's still vertically integrated, they're looking at replacing coal assets, replacing nuclear assets, they're looking to fill a particular slice of what they're doing, then that's going to drive their decisions on how to configure their power plant. You know, what drives us doing merchant plants or merchant-like plants in PJM is very different than what might have driven Exelon at Wolf Hollow. But just a couple observations. We don't currently think that in this market, with the competitive pressures that are out there to drive costs out of plants, we don't see an inherent cost advantage, a construction cost advantage in a 2-on-1 versus 2 1-on-1s when you're up in the HA size frame. The piping is so much simpler and easier to build. It's all straight as compared to what you have to do in the pipe rack on a 2-on-1. Air, especially when they're air cooled, because you know the axial exhaust drives you to ACCs that are pretty manageable. You're not putting a big circ water system in. You're not talking about big towers which get costly. So we've come to the conclusion that the single shaft blocks are a good fit in a lot of markets. You know, and again, it's what basket are you looking to fill? Where do you think you fit into the dispatch stack? What's your forward look of fuel and power prices? You know, is, to this gentleman's point, you know, are you chasing, you know, the last 50 BTUs because you're in a market that's already a low heat rate market, and you're looking to fill a niche? Or are you coming into a market where, you know, you're basically going to replace 10,000 heat rate 40-year-old stuff, in which case I agree, you know, go, you know, build an 8,000 heat rate unit. I quite frankly was surprised that Siemens didn't do better with that Flex Plant 10 product that they had out a few years ago, because I thought it was a good fit in a lot of markets. You know, but you know, it didn't work commercially. So, and then I also think in terms of maintaining efficiency as a developer, again, put the risk where it's best managed. You get a lot of bang for your buck on how do you set up your long-term maintenance arrangements, how do you incentivize the OEMs to maintain performance, maintain output, maintain heat rate. They'll never be in your shoes in the market in terms of risk-reward, but you'll line up those incentives the right way and you have a better chance of being successful of maintaining whatever the efficiency was when you started. So at the end of the day, right, we're all engineers, but you have to be businessmen too.
Just one thing I'll add is that I think with a lot of larger utilities, is sometimes it's human nature to go with what you know. People have been building multi-shafts for a long time in North America, and there's a certain amount of inertia behind it. And you see some of the newer developers or the people more on the cutting edge embracing the newer configurations.
And I'll argue, as a guy that used to work for 2 different investor-owned utilities before I joined the IPP world, you know, never forget rate-based financing is a whole lot more forgiving than IPP financing. So, next question? Yep, sure.
What about the vertical HRSG? I mean, is there an advantage to it in some respect? Never took in North America, so I'm always curious why. Or it's just a moot point.
Footprint advantage, there's a big advantage there. So if you don't have a lot of space, vertical HRSG is good. What we saw when GE was going out purchasing HRSGs before we acquired Alstom, that there was fewer people that were doing HRSGs at that time in F-class size, or vertical HRSGs. So it's just harder to get a good price because there just wasn't as many people making them. Now, I'm not saying it's not a bad, I'm not saying it's not a good solution, but it's just that was the market, that has been the market dynamic up to now. But that could change as well.
Okay. Next question. Okay. Well, if that's it, then the only thing between us and happy hour is me. And I'm going to say thank you so much, guys. It was a great panel.